I'm going to record this session and make it available on our website and our YouTube channel so that people can go back and refer to it. The main thing to keep in mind here, this is the information that's current that I have as of this date, July 2nd, 2014. It may change. The standards are dynamic things. They do change. So I'll keep that in mind if you do go back and look on this webinar again, that it is indeed changes may have taken place, and it's best to touch base with a knowledgeable person to find out what's going on. Okay, let's see. So TrueTech Tools is a stocking distributor of 50 lines. That's my company. Eric Preston and I own the company. Our tagline really is making measurement science work. That's why we're here today, to help you out with understanding what's going on with changes in the industry. We really want to make sure that you pick the right equipment to do your work, largely in HVAC and building performance work. That's our main customer groups. We try to help you learn from us as we learn from you and learn from the industry. Really, we're trying to be a nexus of information. We do the free webinars like you're attending here today, downloads, guides, videos. Much of the information is for free. We do have some books that we sell and resell from some very important networking friends of ours. We're adding new materials all the time. We do offer CEUs currently for BPI. This course does, if you watch the webinar live, and then one individual watches it from one PC, pays attention, does not screen surf, you can qualify for up to one BPI CEU for this. So our main thing is we want to see you do it right. And we want to help you connect across the industry with all the different things that we do. So in terms of BPI CEUs, this comes up a lot. This is kind of just a little bit of housekeeping detail here. One CEU is available for this class. The main thing you have to do is stay on this screen. If somebody's watching over your shoulder, they cannot get the CEU. You will have had to have registered with your BPI certificate number, and that gets logged in along with your kind of viewing habits with this session. I don't think we have any polls today, but that's kind of our standard thing. If we do offer polls, please do answer them. When will you get your CEUs? TrueTech is required to submit the report to BPI in less than 72 hours after the course. We'll probably do it more in the order of 12 to 24 hours. After that point, it's out of our hands. The report, which is generated by the webinar system, goes directly to BPI, and then they process it and will credit your certificate. So after, our steps are pretty simple, straightforward, and we take care of them quickly. After that point, you should contact BPI to see where your CEUs are. And if there's any failure that they did not get the CEUs, please check back and we'll look into that situation. Usually that's not the case. We do get them out quickly. So the thing to keep in mind, this standard is still in draft. The interesting thing I just learned this morning a few minutes ago, when I went to check, I had a link to the standard so you could actually download one and review it yourself. And I found that it was not available or posted online at this point. I'm going to try to find out from BPI if there's a reason for that. Maybe they are kind of in the rewrite stage and deep into it. So I did review an earlier copy about 1 month ago. So things are probably changing, and that's a good thing to see things changing there. That is an ANSI standard, which is the American National Standards Institute, which means it has to comply with all kinds of steps and procedures, the formation of the committee, the nature of comments, the way things are handled. It's a very involved process that BPI has taken on in order to make this standard sort of bulletproof and industry specific and make it work for you and make it be able to be referred to by other codes and regulations. The initial public review did close back in November, but my understanding is that it will be out for another public review this summer, which means pretty shortly since we have passed the summer solstice. This standard is not yet put into practice, but it's my understanding they've circulated it to trainers, and they want trainers to be training to Section 7. And that's what we'll be talking about, of course, is the diagnostic measurements, which are in Section 7 of the standard. Actually, breaking news right now. BPI has responded. They said they should have had the standard up on the website, and there's one available. So the one that was posted previously. So they're going to get back to me, and then we'll make that available through some kind of link. which I will send out to attendees of this webinar. Just making a note here. I'll send a link to the standard 1200 so you can take a look at it. So an ANSI standard, sorry for those of you that are offended, maybe vegetarians or whatever, offended by this, but it's like making sausage, like a lot of things. You have to take an awful lot of information and grind it together and make it into a palatable product that can be used by the public. There is actually a procedure that BPI follows that is ANSI compliant. If you're interested in that, you can dial into that address there. When you use these bit.ly short links, make sure that you obey the upper and lower case that's there, but that's BPI's procedure for creating an ANSI standard, and it's been approved by the American National Standards Institute. The National Technical Director is John Jones for BPI. He oversees the standards, all the development activities, ensures there's compliance with them. That's his email address there. That's the main guy I've been talking with, known him for years, a great guy, and he's the guy that's got this heavy responsibility to make sausage. It's a consensus standard, which means all parties have to agree and come to agreement on what will be presented and have to understand, all the different parts of the industry have to understand each other. It does reference other standards within it. Usually also ANSI standards are referenced. So it's sort of a composite. It does something unique for itself. It doesn't rewrite standards if things are already in existence. It is very tough work, and I do want to jump out of here, the presentation, and jump into the committee list to show you here, just in a web browser. This is from the BPI site. The working group number 7, Basic Analysis of Buildings, BPI 1200S. You can just take a look here and sort of see the list of really celebrities that are working on this standard, that have taken part in this. So it really does cover a very large cross-section of the industry. You can see people from national laboratories, people from practitioners, BPI practitioners, energy commissions, membership organizations, independent consultants, manufacturers. So it's a very, very broad type of consensus standard. So we'll go back to this and talk about our focus today. And that's in section 7. And this is basically a little recap of the index here. There are 12 different sections and 2, 4, 6 annexes that are also part of in either informative or normative. And just if you're not familiar with standards language, normative means it actually states something that's important to the standards and helps people norm or come into understanding with the standard. Informative annexes are those that just explain things. They're not really part of the standard, but it's often put in there to be helpful to explain people and how to go about complying with the standard. They aren't required. Informative ones are not required. Normative ones are required for compliance or for understanding. So again, we'll be talking about combustion appliance and fuel distribution systems inspection. That's the main area we'll be talking about today. And again, if you're not familiar with standards, you do have to watch the wording. When a standard says shall, it's a mandatory requirement. Another way of interpreting that is you must. You must follow, you must do. May indicates permission. It's not a requirement or a recommendation. It's just something that you should consider in your work process. First topic we'll cover are CGDs, which are combustible gas detectors. Right now, the standard states, and these are lines that are pulled from the current draft standard that's available or soon will be available again on the BPI website. It says a combustible gas detector must be intrinsically safe. This definition of intrinsically safe here is one which, I'm just going to move something around my screen here, one which will help you understand. It basically, intrinsically safe means the equipment or the product, the meter, whatever itself, does not have enough energy in it under any kind of conditions, normal or abnormal, to cause ignition in a certain kind of atmosphere in its most easily ignited concentration. So it makes it really ultimately a safe product that intrinsically in and of itself is safe to use in explosive atmospheres. So this is achieved by limiting power that's available inside the equipment. So it's done by design that makes it part intrinsically safe. Um, Other aspects of it are maintenance and replacement and service has to be done in a proper, certain manner. So these are all important things to keep the product intrinsically safe. So it's basically it's something that's inside the product, the way it's designed. It must be maintained and serviced in that way in order to keep it intrinsically safe. So it would comply with this statement for the standard. And again, intrinsic means by design. And that also includes must be used as designed. So there's some usage requirements the manufacturers will have on these products and how to use them that must be followed to keep this whole concept of intrinsic safety in line. So to understand intrinsic safety, I just want to take you a little bit further into the science so you understand why this is being required, why this is being asked for. In order to have a fire or explosion, you must have the correct quantities of fuel, oxygen, and thermal energy or a source of ignition, heat, flame, spark, to ignite the mixture. So this basically gets back to some of the things you probably learned in combustion class or combustion training if you're taking it. So sometimes you hear about the combustion triangle, where there's fuel, oxygen, and a source of ignition, source of energy in the right quantities can lead to combustion, or in this case, explosion. So it's important about the right time, the right place, and the correct quantities to have this happen. So an intrinsically safe product assumes that you have two of these items, the fuel and the oxygen, in quantities that can lead to combustion or can lead to explosion. It assumes that that could happen, and therefore it limits the thermal energy in the product or the electrical energy so there can never be enough energy. So it controls this one leg of the triangle. That's what an intrinsically safe product does. That's what it brings to the game. So there's various brands and models of combustible gas detectors. One of the listing points on the standard is that it must have an adjustable tick rate, and that's achieved in different ways um, through an adjustable dial or a thumb wheel, like in these two products here on the back right Leacator 10. Um, Leacator Junior has a high-low level switch. The Sensit TKX has a thumb wheel or dial on it. Or on the Sensit HXG2D, um, the tick rate can be controlled. That's the adjustable tick rate. So there's different means of control, or some kind of resettable tick rate has to be available in order to go from high to low and to do that kind of sniffing or ferreting out situation. Um, just having some people with technical difficulties. I apologize, but it looks like it's the GoToMeeting system, and the session is being recorded and will be available if someone is missing it right now. So, getting back here, we're talking about relative, not absolute concentrations, but relative concentrations are what's required from the combustible gas detector. You can get a model, such as this one in the center of the screen, that has an absolute or a measurement in it, but that's not required. It's just looking for relative. There was more here, there's less there. You can tell by the tick rate. You can adjust the tick rate to tell whether there's higher and lower concentrations of gas. The standard also, at this point of review, also requires an LEL alarm. We'll get into what LEL means a little bit more completely, but it stands for lower explosive limit. So what the standard is looking for right now in its present state, and again, things could be in flux, things might change, but the combustible gas detector should provide an alarm when detecting concentrations exceeding 10% of the lower explosive limit, which is 0.5% concentration in air by volume. That would be like 5,000 parts per million uh, by volume for methane gas, which is the most typical gas. Um, that, however, is a different amount of gas for propane. So that's one of the feedbacks that I've given and other people have given to the standard. So we want to make sure that it's correct across all types of fuel gases, and the two most common in use are methane and propane. So really what they're looking for is 10% of the lower explosive limit. There should be an alarm that goes off to tell you that there's that concentration of gas in the area, in the vicinity. Now let's take a look and understand what this lower explosive limit means kind of in the real world. What is the science of it? If you look at it from the standpoint of the concentration of gas, if you look at the chart, the graph on the left here, the concentration increases from 0% gas in air, so there's no combustible gas in the air, up to 100%. As you move from 0 to the lower explosive limit, that's the limit at which the mixture of gas in the air, in standard air, at this point could start to support combustion if there was a source of ignition applied to it. It actually moves through a range, this dangerous range, and then above a certain point, there's too much fuel for the oxygen in standard air, which has 20.9% oxygen in it. There's too much oxygen, too much fuel for the oxygen that's available, so it cannot support combustion. Uh, this is green because it's considered more safe, red because it's dangerous, and yellow because there's a caution. Because as soon as it moves from this too rich or above the upper explosive limit, and it moves back down, and the gas concentration drops back down, it can drop back through into the combustible range just by dispersing or having the source of supply set off, or the gas cloud moving through an area. So it can drop from the upper explosive limit into the explosive range before it gets to below the lower explosive limit. So that's why we want to pay attention to these two levels, upper and lower explosive limit. And usually, in most situations, we want to constrain ourselves to being below the lower explosive limit. It's also sometimes called the upper flammable limit, or the UFL. That's an area above which it's too fuel rich. The concentration of the fuel gas in the air is too fuel rich to burn. Not enough oxygen around. Within that range, the red area, it could burn or explode if an ignition source is introduced. And then below the lower explosives, or the lower flammable limit, it's too lean on fuel to burn. There's more oxygen available, and there's not enough fuel available for combustion to light off. So the LEL and the LFL are pretty much interchangeable terms. Most usually I hear LEL, lower explosive limit. Of course, the UEL and UFL are interchangeable terms, but usually, again, it's usually the upper explosive limit. Okay, so let's take a look at measuring gas concentrations and just get into a little bit more of the measurement science here. The typical unit of measurement is a part per million. It's a volume concentration. It's how many parts in the whole, how many parts are in the sample. It can be expressed as a percent LEL or percent UEL. Again, ppm can be converted to percent LEL or percent UEL if you know the gas, because propane and methane have different explosive limits. And just for reference, 10,000 parts per million is a 1% level by volume. And a parts per million, again, can be correlated with a percent gas. Let's move on to the part of the standard, and these numbers here are the current numbers that are in the standard. So if you wanted to refer back to them, you could see where this verbiage is coming from. This talks about calibration. Calibration, what they're looking for in the standard is calibrated in accordance with the manufacturer's recommendation, or annually, which is ever of greater frequency. I have a little difficulty with this because the Leakator 10 manual, the manufacturer says, does not require calibration at regular intervals, which sort of makes a little point of confusion here. How can you calibrate it if the manufacturer says it does not require calibration? These are one of the spots that we believe BPI is going to get corrected here very shortly with the next release of the standard. Also, the detector should be labeled with a calibration sticker noting the last date of calibration. So that's a pretty simple or straightforward requirement there. Zeroing, that's another part of the standard, 7.2.2.6, zeroing of the combustible gas detector. They're looking for the product to be able to zero out ambient conditions. The reason for that is you're looking for a change in concentration. You're looking for the source of the concentration. So you want to be able to null out or correct for or to ignore, say, the current value as you move towards the higher value, the higher source. So it's done in different ways. In some It's done by an adjustment, like the thumb wheel on the two products that are on either side here. And in the center product here, the digital meter, it's done via a button, which allows you to zero out the background level. And just wanted to cover another topic because it does come up a lot. What if I smell gas? How does this relate to if there's gas present by virtue of one of the sensors that you carry around with you on the front of your face, your nose? Uh, Actually, natural gas does not have a smell. Um, it is actually has an odorant added to it. It's not detectable by the nose in its normal chemical compound state. So the odorants are chemicals that are added to the natural gas in the processing, in the delivery process. It's usually methyl mercaptan. It produces a kind of a sulfury smell or smell like rotten eggs, which can be detectable at very, very low levels. However, kind of the rub here is it can still be detected. The odorant can still be detected at 0.1 part per billion, which is a millionth, a thousandth of a parts per million is a part per billion. Even though the gas is dissipated, the odorant may still be detectable. So some of this commentary developed here came from some fire safety bulletins that are out there from some of the manufacturers and others that are in the fire safety industry where they have to deal with these kind of gas emergencies very often, utility industry. So an odorant is not the be all and end all of gas detection. So don't assume or think that it's there as a public service, but it's not meant to be the be all or end all or to rule out a meter that's used to detect. So from all of this, even though it's done as a public service or as a courtesy, noses are not accurate detectors. Some people cannot detect even the methyl mercaptan smell at the same level. So there's a very wide ranging response by the human body to the odorant. So they're not meant as a accurate indicator. And also there's a concept called olfactory fatigue, which basically means you smell something long enough and it doesn't smell anymore. It doesn't react anymore. So this all sums up to odorants are not to be relied upon as a measurement. Okay, so what are you looking for in a combustible gas detector if you want to comply with this BPI 1200 standard the way it exists right now? So we'll just go back and pretty much recap. We're talking about intrinsic safety as it's written right now. And that boils down to looking for a product that has the UL 913 rating for Class 1 Division 1's Group CD at a minimum, but it could also be A, B, C, and D. Uh, that means that's the type of gas, the type of environment, and it's a standard written by the Underwriters Laboratory, UL 913. If you see this mark on the equipment, then you would be in compliance with the intrinsic safety concept of the BPI 1200 standard. So this is just to give you what it looks like from one of the manufacturer's literature. This is lifted right from their instruction manual from the Sensa TKX, which is one of the really popular leak detectors that we sell here at TrueTech Tools. It talks about the UL 913, Class 1, Division 1, Group C and D, in hazardous locations when used with a Duracell MN 1400K or equivalent alkaline battery. That's a very interesting comment. We talked about design, maintenance, service, the way you use it. It's been tested to comply with this kind of battery. Other batteries may not have the same kind of compliance rating. So again, if you want to maintain your intrinsic safety, you have to follow to the letter what the manufacturer asks you to do with the product because your usage, the batteries you use, the service you use, the way you use it is all part of the design of this intrinsic safety concept. The other important parameter you need in your combustible gas detector is an adjustable tick rate. It needs to provide an alarm above 10%, a calibration sticker, and the ability to zero it out. Just want to make sure, this is one thing that came up at a recent trade show at the ACI trade show and actually Resonant too. There's a confusion over the 10 part per million threshold. Some people were confusing the minimum sensitivity level, which actually is not covered in the standard. If you look back through it, and I did, believe me, it's not. They don't talk about minimum sensitivity. Some people have read this 10% LEL alarm and interpret it as being the detector has to be able to sense down to 10 parts per million. That's not true. That's not in the standard. Manufacturers may state that their detector, their combustible gas detector, senses down to 50 parts per million or 100 parts per million or 20 parts per million. That's fine, but that's not a requirement from the BPI 1200 standard. So don't mistake this 10% LEL alarm with anything to do with minimum sensitivity. That mistake is being made an awful lot there. I want to make sure we dispel that and clear that up. The next standard category, or the category for diagnostics, is CO measuring equipment. We're talking about CO, carbon monoxide. That's what's shown on the screen there. One of the key specifications in 7.2.4.1 is that the range of the carbon monoxide meter needs to be 0 to 2,000 parts per million. So that's pretty simple, pretty straightforward, pretty easily met by pretty much all the equipment on the market that's used for flue gas testing. There's another part of the standard which requires 7.2.4.2 CO air-free measurements. Here's information lifted directly from standard, shall be capable of measuring and displaying on a digital display air-free CO concentrations directly. Since normal air has a concentration of 20.9% oxygen, the CO air-free calculation by my math, and I've done product development, have some patents on different products, usually says we're usually looking at values up to about 10,000 parts per million in the calculation. So I'm pretty sure that that statement that's lined out there will be lined out from the final version of the standard. So we're talking about basically CO air-free concentrations, and it's probably going to say up to 9,999 or some level like that is the concentration range for the CO air-free calculation. Some products call CO air-free CO undiluted or undilute. That means it's doing a calculation to remove the impact of the diluting air, the air that gets in to the flue gas stream either through the combustion chamber or through draft assist or through ventilation air, combustion air, that would throw off the CO calculation, just the raw CO number by diluting it. We're going to get into this concept in the next slides here to sort of kind of crack that open and explain the science behind the CO air-free calculation, what it means and how it's going to work. One factor I do want to mention here is that just to make sure the word undiluted or diluted sample means something different than the calculation CO undiluted. That's got to be made clear. Usually we're looking at making measurements in an airstream that's undiluted. That means before any kind of draft diverter. So that's one notion. The other notion is we're talking about an undiluted calculation where it removes the diluting elements from it. So don't confuse an undiluted measurement versus a CO undiluted calculation. Probably have to work a little bit more on that. We actually have another webinar strictly on CO air-free where we kind of slow down and break this down a little bit further. It does also qualify for 1 BPI CU if you watch it live. So that's also available. I'll show you that on our webinar calendar before we leave the session here today. Okay, getting back, we'll get into this combustion diagram and try to develop the concept of CO air-free. So this is part of our combustion seminar, again, which is coming up if you want to hear like a more lengthy explanation of the whole combustion process. The stoichiometric line is basically the balance point of combustion, where the chemical equation balances, where you have just the right amounts of fuel and oxygen to get perfect combustion and the perfect byproducts of combustion. So on either side, you have either incomplete or not enough fuel for the air available, or complete combustion. So we have either excess fuel or excess air. In some ways, this actually mirrors that concept of reaching the lower explosive limit and upper explosive limit. So there's that kind of notion that's still in here with the amount of air changing, the quantity of air or oxygen available. Here's the line of increasing oxygen. So this is basically what would be happening to your meter if we were able to dial in and change things, either the amount of fuel or the amount of oxygen going into combustion. We were to change, so you'd get variable conditions. So what would it look like if we were changing the amount of air going into combustion? The interesting thing you'll notice here, or at least I think it's interesting, is that oxygen starts out at zero at the stoichiometric line. We're getting no residual oxygen being measured by the combustion analyzer because there's not enough to go around. There's too much fuel for the oxygen available here, so it's all getting used up. Beyond the stoichiometric line, there's enough extra oxygen left over that you can start to detect and to measure it. So that's what's going on here. That's why oxygen rises when you're on the right side, the complete combustion side, the stoichiometric line. Here's what happens to carbon monoxide concentrations. Um, High amounts are made here because there's not a lot of oxygen available, and increasingly lower amounts are made, and then it actually begins to be diluted and change at a more rapid rate as it comes down the line here. That's happening. It should have a higher slope. In fact, I'm going to go back and try to correct that slide using my great PowerPoint skills. But it actually is being diluted here by the oxygen. There's oxygen available, which is going to change the concentration. Again, how much CO is available in the sample is going to be changed here because there's excess oxygen, excess air in the system. So it's going to change this level basically due to dilution of the oxygen. So if we could magically remove that oxygen, we would see CO air free as one continuous number across the screen. And that would be independent of how much oxygen is available. You would have a CO air free reading. I believe this is the reason why BPI has approached this point. It makes it less sensitive to conditions, to the amount of air going through. So you'd be able to look at this one kind of ultimate level of CO production. The interesting thing to note here is no matter what the excess air situation is here, moving to the right, it's going to be the same level of CO air free. And the CO air free number will always be higher than the raw CO reading. Okay, so that's another thing to capture from this graph, is that the CO air free number will always be higher than the raw CO because it's being diluted, the diluted CO reading. So the calculation is here. It's basic science that the combustion analyzer is using. That's the CO raw. That's the number that's measured by the sensor. 20.9 comes in there because that's the standard concentration of oxygen in the atmosphere, and the O2 reading that's coming from your O2 sensor. So from this, you can very quickly derive that in order to make a CO air-free calculation, you must have a CO sensor and an oxygen sensor, which means a product that only has a CO sensor in it would not be suitable for CO air-free calculation. You either have to have another oxygen meter or some way of measuring simultaneously and dynamically the same calculation, the same parameter, oxygen and CO at the same time. Usually this means you need a combustion analyzer because they typically contain 80, 90, 95% of them contain CO and O2 sensors together. This calculation here, we'll take a look at a little calculating spreadsheet, which I'm still in the refinement stages of, but plan to circulate it to people once I can get through my quality control checks on the spreadsheet and make sure it's pretty bulletproof for everybody to use. But I'll show you a working prototype of that spreadsheet. I know a couple people out there are hankering to get their hands on it. Most analyzers do stop the calculation over 16 to 18% oxygen because it gets so close to ambient air conditions, it's really not a flue gas type measurement, and it's pretty high numbers are involved. So let's take a second here and we'll jump out and take a look at Bill's spreadsheet. And here it is. This is the carbon monoxide air-free calculator. It allows you to do a couple different things to look at CO in different ways, and I've gotten a couple feedbacks. That's the other points which I'm trying to change in here, as well as do the quality control. But if you had a level of CO, say 100 parts per million CO, and you had an oxygen reading available, there's a factor we call developed, that's part of that little equation there, that would lead to a CO air-free reading thusly on the right-hand side. So at 0% oxygen, because it is then CO air-free, it would correspond with 100 parts per million. So that would give you the same raw CO as the CO air-free reading. But as you get into higher percentages of oxygen, you're working with a dilution. That oxygen is diluting the concentration of CO. So if you were to back it up to that stoichiometric wall, kind of walk backwards towards that wall that we showed in the previous graph, you would have a higher level. So again, CO air-free is always equal to or higher than the raw CO reading. And as you see, as you get up to higher levels, say like 10 parts per million, or excuse me, 10% oxygen. Sorry, I got to sneeze. Okay. At 10% oxygen, the CO air-free factor is 1.9, or it'd be about 192 will be your CO air-free reading. And so we're typically talking in oxygen levels that are in this range of 5 to 15% oxygen. So you can see there's quite a large multiplier that can get into the 1.5 to 2 to 3 to 4 to multiply your CO reading. Another way to look at it, this is a dynamic calculator that just produces results. You need to give it two inputs. So this would be like you're inside the brain of the combustion analyzer, and you're giving it 100 parts per million CO is coming from the CO sensor, and then 8% oxygen is coming from the oxygen sensor. The CO air-free calculation that would pop up on that line in your screen would be 162. So this is a way of kind of figuring out how these things work inside the combustion analyzer. And then this little static chart down here is the standards pretty much we talk about is 400 parts per million CO air free for most appliances. So I just did a little kind of backwards calculation and say to get into the range of around 400, what oxygen reading would you need and what CO combination would lead you to that point? So of course, because it's two factors, it can be a blend of these different things. Anywhere from 0% oxygen and 400 parts per million would lead to 400 CO air free, anywhere down to, and this is kind of ridiculous, but 10 parts per million at 20% oxygen would lead to 400. Typically more in the range of, say like 11 to 13, but at 150 parts per million, 13% oxygen, you'll be up there in that range of 400 parts per million. Again, working on some final details and some quality control in this calculator, and then we'll make it available as a download somewhere. We'll make it available, this locked Excel sheet available as a download for you. Okay, let's return to the presentation and go back to the kind of pull out and summarize the parameters we're talking about, what to look for in a carbon monoxide measuring instrument. We're looking for a range of 0 to 2,000 parts per million on a digital display. Pretty easy requirement to meet. We're looking for CO air-free measurements. That kind of locks you into pretty much combustion analyzers. So I'm going to name some names here, but things like Monoxer 2s, Monoxer 3s, Monoxer Pluses would not qualify as a CO measurement tool for this BPI standard because they do not have oxygen calculations. So it must have a CO and an oxygen sensor present. You could use one of those tools I mentioned previously and use an oxygen sensor or an oxygen analyzer and do the math offline yourself, but you're pretty much in a situation where it's difficult. You made things difficult. I'm going to remove that second A there because it's bothering me. Okay, sorry, I'm recording this too. Great, huh? Okay, also looking for 1 ppm resolution and a 5% accuracy. That's another requirement that's in the standard. And there is something that's not currently in BPI 1200, which I'm encouraging BPI to look at, but looking at the fact that I believe there should be a NOx filter or nitric oxide filter for the CO sensor. NOx comes usually from nitrogen in the air. Air is about 78%, 79% nitrogen, or can be bound in the fuel or other things, but mostly it's air, nitrogen in the air, oxygen in the air can chemically combine in the combustion system to produce nitric oxide. Nitric oxide tricks a CO sensor. Again, we'll get into this if you want to attend strictly the CO air-free measurement session. We'll get into a little bit deeper. But this is just a little illustration here, which shows you at a level of 40 parts per million NOx, which is these two instruments are sampling the same flue gas stream from the same piece of combustion equipment. at a level of 40 parts per million NOx is measured here. And again, we're not talking about measuring NOx, but the impact of it. So we measured it here, and we found that that led the CO sensor to be off by 21 parts per million. Because the actual CO, and this is with a filtered CO sensor, one that's filtered for NOx, reads truly and actually 6 parts per million. That would lead to a mistake in your calculation of CO air free, so it kind of propagates and makes for incorrect measurements. So pretty much now all the manufacturers do have a means to, just to point out here again, that the actual level actually is 6. This meter here is reading 27 because it does not have a NOx filter, and you have about 38 ppm nitric oxide present. That's what's leading it off. Most manufacturers either have built-in NOx filters or provide them outboard. We do sell a brand we've sourced at TrueTech. It's a very cost-effective brand called Correct Measurements. I believe it's $39.95, including free shipping. So if you don't have one in your meter, you can splice it into the sampling line, the sampling hose, and you can be using a correct measurement, basically, for your CO reading to cancel that NOx. Again, if you want to learn more about it, take a look at that bit.ly link down at the bottom on the page there, bit.ly/NOxTruth, all uppercase, or attend the session. We'll be doing the webinar live in a few days regarding CO air-free measurements, and we'll get into this too at that point. There's also a line in the standard, section 7, 7.2.4.7, that talks about CO measurements from a personal safety standpoint. The standard as it exists right now says the equipment shall not be used for personal safety unless it is certified by the manufacturer as suitable for personal protection. I've never actually seen this certification myself, so I'm looking for clarification from BPI. And again, this may be one of the points where they change the standard in its current phase and its draft and review phase. For this industry, you don't usually see it certified by the manufacturer. So when you get into a little bit deeper into the personal CO monitor, 7.2.5.1, the statement is auditors performing CO inspections shall have a personal CO monitor approved by the manufacturer for personal protection. To me, personal protection means that's pretty much an industry standard, kind of from earlier back in my career, where it talks about the Occupational Safety and Health Administration and the Code of Federal Regulations, subchapter 1910, 1910, where it talks about personal protection, personal safety for industrial environments. So there's a little bit of clarification, which I'm looking towards BPI to provide there, and I think they're coming up with that to make sure we get the right thing for this industry. This one standard here would actually rule out the use of a Testo 317.3 or a Fluke CO 220 for the reason that the manufacturers actually say do not use for personal safety, do not use as a personal safety monitor. These are excerpts from the Testo and the Fluke instruction manuals. So I think BPI may be going back and looking at this statement to see if that's really what was intended. So some other details. 7.3 talks about safe entry and working conditions associated with indoor air quality. Outside zeroing or calibration in 7.3.1.1. And then talking about time-weighted averages for CO. There is the standard does have these reversed in the draft standard, which is, I believe, is a typo for these time-weighted averages. The other impact here is that the time-weighted averages require some means in your personal CO monitor for monitoring, recording these time-weighted averages, because CO is a cumulative poison, and for reporting and alerting to these levels, which would put you again in another class of product. So these are some issues that they're kind of wrestling with to determine if this is really where they want to go with it. Keep in mind this is a draft standard, and there's going to be more public review and more comment and more feedback to make sure this is where they want to be with it. Again, it's a process. So I'd like to entertain any questions anyone might have. I hope you're familiar with the question box in the control panel that you have on the side of your screen. I'm not seeing any questions come up here. I'll wait a minute for those questions to come in, and we'll just cover a couple more points, and then I'll stop the recording. Um, for future webinars, I am going to give you just a little preview on that. I will show you where that is on the TrueTech website. If I could only type. This again is being recorded for all of humanity to see. If you go to our resources page, resources tab, click on the webinars link. And I do see questions come in, and I will get back to that in just a second. But here, truetechtools.com/webinars, you can see our webinar calendar. If you just click on any of these, for example, in this 4 p.m. on the 10th of July, Understanding CO Air-Free webinar, just lift this link right here, paste it into a browser, and sign up for the webinar. And feel free to share the link, let people know about it, or bookmark this calendar page. But we'll be keeping track. We have another one on combustion coming up on the 15th of July and airflow on the 30th of July. And again, I'll get to that question in just a second. And here is the resources page, truetechtools.com/resources, where you'll find we've collected all our training materials, our videos, etc., into one place for you to keep track of. And this is how you contact us. I'm going to stop the recording now and go ahead and answer that question. Actually, I have a raised hand. What I need you to do is ask the question, please. If you can, type it in the question box.